Welcome to the next session of quantum dynamics. So today we will give a brief review of harmonic oscillator. Okay, so harmonic oscillator, as you know, it is the simplest oscillator in physics, and usually it is called a simple harmonic oscillator. Okay. Now, what is a simple harmonic oscillator or what is an oscillator? The oscillator is a physical system which always have a to-end formation. And to-end motion will happen about some equilibrium position. So there are three different equilibrium we have: the stable equilibrium, unstable equilibrium, and neutral equilibrium. So the oscillation would happen only at around the stable equilibrium position. So therefore, the simple harmonic oscillator is a to-end motion about the stable equilibrium position. Stable equilibrium. But there is one more condition. Because not all to-and fro motion about stable equilibrium position is not a simple harmonic oscillator. So the oscillation is called simple harmonic only if the restoring force experienced by the system, okay, so consider a one-dimensional problem. So restoring force experienced by the system is proportional to, is linearly proportional to the displacement. So if the restoring force is proportional to displacement, then the oscillator is called simple harmonic, and moreover the restoring force would always be against the displacement. So that is why a minus sign I put over here, and a constant k is called the force constant. Okay, now why it is important in physics? Because in physics there are, we'll experience many kind of oscillator like simple pendulum, or the oscillation of a spring, or the oscillation of a ball around the valley. Okay, so there are many physical systems which is having the oscillation problem, and in the simplest sense, the oscillation, any oscillation, we can treat as the simple harmonic oscillator. Okay, if you add the complexity, then it may become an harmonic or a damped harmonic or forced harmonic, that depending upon the system. Okay, so the simplest way of solving any oscillation is treat it as the harmonic oscillator, and there are certain conditions to treat an oscillator as a harmonic oscillator that I will discuss very briefly. Okay, now in general, the potential experienced by any system I can denote by symbol V of x. Okay, now so consider some system. Okay, particularly I will consider a ball which is moving on the surface of Earth. Now while moving on the surface of Earth, sometimes it may have to climb a hill. It may move towards the valley. Now it may experience a flat region. Okay, so when a ball is moving on the surface of the Earth, it will experience many different situations. Okay, so I will take one simplest case of such potential. Okay, so this point is my origin. So I am going to draw the potential experienced by the ball on the surface of Earth. About on surface of Earth. Okay, maybe like I am just noting like this. And this axis is symbol x, a displacement from some point O. So this 0 is origin. Okay. Now, if you look at this graph, there are three different equilibrium positions, or three different regions of equilibrium. So one is this point, another one is this point, and about this region. All these are the equilibrium region. Now what is equilibrium? The equilibrium on the point with force 0. So if the force is 0 about some point, then that point is called the equilibrium point, or if the force is 0 in a region, in that region is called the equilibrium region. Okay, now if you look at this point, I will not by symbol some x1. Now the x1 point is an equilibrium point, but it is not a stable equilibrium. Because if the ball is kept here, it will not experience any force at all, it will remain there forever. But if you displace it slightly from its equilibrium position, it cannot come back, it will not return, it will go forever from that point. So therefore this kind of equilibrium is called unstable equilibrium. And we know how will you find the position of unstable equilibrium mathematically. The mathematical thing is the first derivative at the unstable equilibrium is 0 and the second derivative would be negative. So that is the characteristic of unstable equilibrium. The first derivative is 0 and second derivative of potential would be negative. And this point, again if you keep the ball at this point, it will remain forever. But if you displace it slightly and if you release it, it will come back to its original position. So therefore this equilibrium is the stable equilibrium. And the condition is if the first derivative would be 0 and second derivative is positive because it increases from negative 0 to positive. And this region again is the equilibrium region because if you kept the ball here, it will remain there forever. But if you displace it from its original position to a new position, quasi-statically, then it will remain to the new position. It will not come back. And hence, it's called neutral equilibrium. Okay. Now the main point is the oscillation would happen about the stable equilibrium position. If you displace the object or the system about the stable equilibrium position, it will go for to and fro motion. Now how it is to and fro motion? Because if you displace it slightly from this point to the new position and if you release it, it will come back, but while coming back it will acquire some kinetic energy. So although the particle return to the stable equilibrium point, it cannot stay there, it will rebound to the opposite side. And it will climb some height in the opposite direction. Again it will stop there for a moment, it will come back, then this motion will go on, this to and fro motion will go on, and such motion will be called oscillation. Now when this oscillation is called the simple harmonic, the simple harmonic will happen if the force acts at this criteria. Okay. Now we can have a simple condition. What are the conditions to treat this oscillation, the simple harmonic oscillator? For that I am going to expand my potential V of x about the stable equilibrium. Now I am denoting the stable equilibrium as x0. I am denoting my stable equilibrium position as x0 and I am going to expand my V of x about x0. So V of x I can expand about x0 as V at x0 plus x minus x0 V prime at x0 x minus x0 square by 2 factorial V double prime at x0 and so on. So this is the famous Taylor expansion. Okay. Now while drawing this graph I carefully chosen the potential at x0 as 0. Okay, so even if you don't drawing this way, you are having always a freedom to choose the 0 of the potential at any point. That doesn't matter because what physically observable is, what physically experienced is the force, which is the first derivative of the potential, and this V of x is V of x0 is always a constant. So if you take the derivative of the potential, the derivative of the first term always becomes 0. So whether it is a constant or whether it is 0, that doesn't matter. Okay, so since this doesn't matter, that is why I have already chosen the potential, the stable equilibrium position is 0. So I have chosen it very carefully. So this becomes 0. Otherwise, if you have not chosen it initially, then you can choose it later as well. You can always choose the V of x0 as 0. That will not change any physics. Okay, now what would be V prime at x0? V prime, the first derivative of the potential, and x0 is the stable equilibrium, and the first derivative of the potential about the stable equilibrium or about any equilibrium would be 0. So V prime at x0 is 0. Okay, so then that means the first non-zero term would be the third. Okay, and obviously there will be higher order terms as well. Now, if you look at this x minus x0 would give the displacement of the particle about the equilibrium position. Now, if that displacement is very small, then the next term, the third order term would be very small compared to the second order term. So that means I can neglect the higher order terms if x minus x0 is very small. So if x minus x0 is very small. Then after this, I can write my v of x as half v double prime at x0 x minus x0 square. Now, in order to compare this with our original equation f of x equal to minus kx, what I am going to do is I will choose my stable equilibrium position as my origin. So right now my origin is here. Okay, now I have a freedom to choose the origin at any point. Okay, so instead of choosing the origin here, I am going to choose my origin at this point. So instead of this point as x0, I will be choosing as that point as 0. So I will be choosing x0 as my origin. Then my v of x will take the form half v double prime x0 x square. Because x of this. Okay. Now what will be the force? So force f of x will be minus dv by dx, the first derivative potential with respect to x. And if you do it, it will be minus half v double prime of 0 is constant, and if you differentiate x square, you will get 2x. The 2 will cancel, it will be minus v double prime of 0 into x. Okay. Now this is the general form of the force on a simple harmonic system, f of x equal to minus kx. And you can identify v double prime at 0, there is second derivative of potential about the stable equilibrium position is nothing but the force constant. So v double prime 0 is nothing but your force constant k. Okay, so then this potential I can call the potential of the simple harmonic oscillator. The potential of simple harmonic oscillator, and this is my force. And you can identify this v double prime at 0 as my force constant k. Okay, so we can solve this problem in order to find what are the possible energy and what is the explicit form of the position and momentum, etc. And for that, the thing is very simple. You can solve the Newton's second law, which is a second order differential equation in time. So this f of x equal to minus kx. So f of x equal to minus kx, you can rewrite in the form of d square x by dt square equal to minus omega square x, where omega square is equal to k by m. Okay. So f is m d square x by dt square. You can take m to the right side. You will get k by m, and I am going to denote this k by m as omega square. So d square x by dt square equal to minus omega square x. And if you solve this, then x would be either a sine function in time or cos function in time, because if you differentiate x with 2 times, you have to get x back with a negative sign. So that happens when x is a sine function or cos function, because if you differentiate sine 2 times, you will get negative sign. If you differentiate cos 2 times, you will get a negative sign. And moreover, there should be some omega square. So it should be the argument of the sine or cos must be some omega t. So x in general may be some in the form of a cos omega t plus b sin omega. So this should be the general form of x. Okay. So this is a way of solving the simple harmonic oscillator using classical physics. And finally, on solving this, I can find what is the potential energy and what is the kinetic energy. Kinetic energy can be found by differentiating this x with respect to time, because that will give this velocity, and half mv square will give the kinetic energy. And if you sum the potential energy plus kinetic energy, you will get the total energy. And the total energy of the system, the classical oscillator, will take the form half k square. So this is the important point that I would like to make. Okay, so for simple harmonic oscillator, energy is a continuous variable. So here a variable A comes over here, and A is amplitude, which is the maximum displacement an oscillator can take. And it is a continuous variable. So there is no restriction, there is no discreteness for A, there is no randomness for A, and therefore there is no randomness for energy. So energy can take any value between 0 to a maximum value. Okay, again remember, this A cannot be very big, because in order to treat the oscillator as a harmonic oscillator, this x minus x0, that is the displacement, must be small. So that means the maximum displacement may not be very huge. So the A cannot be very huge quantity depending upon this, the limit of the A depending upon the size of the system. Okay. Now depending upon that, the A should be small. And moreover, but the remarkable thing is, even though A is small, the A can take any value within the limit. Okay. So A can take any value. So therefore the energy is a continuous variable. There is no discreteness in a classical oscillator. So whether you have a spring mass system or a simple pendulum system or an oscillation of a ball about the equilibrium position in a valley, so in all of this system, the energy of such classical oscillator can take any value. So with this we have completed the discussion of the problem of harmonic oscillator in classical physics. So we had a quick review of harmonic oscillator, the simple harmonic oscillator, which is the simplest problem in physics. And if you have more details, we can add the details to this problem. That is, we can include the higher order terms to the potential, and if you include the higher order terms in the potential, then the oscillation will not be, it is not called the harmonic oscillator, it is called anharmonic oscillator. And if the damping is present, then the oscillation is called damped harmonic oscillator, etc. So basically this harmonic oscillator is the simplest oscillator that we can solve. So if you have any oscillation problem, we can, on the first order, we can treat all such oscillation as a harmonic oscillator. And for classical physics, the harmonic oscillator, the energy of harmonic oscillator is continuous. There is no discreteness. Okay, so next we will treat the same problem quantum mechanically. And while we are treating the same problem quantum mechanically, only thing will be required is the form of potential of simple harmonic oscillator. So once you know the form of potential of simple harmonic oscillator, we can solve it quantum mechanically, because in quantum mechanics we will not use the concept of force. Okay, so only the concept of potential we require. So that we will discuss in the next session. So in next session we will illustrate the solving of harmonic oscillator using quantum mechanics. Next, I would like to pose one question to you. The question is, why the harmonic oscillator is important in quantum mechanics? In classical physics, we know there are many real life examples. The simple pendulum, the spring mass system, the ball oscillates around a value. There are many real life examples in classical physics. Do we have any real life example in quantum physics which act as a simple harmonic oscillator? You should think about it. You should come up with an answer in next session. And next session, I will solve the simple harmonic oscillator using Schrödinger. Thank you.